So as I said earlier, when we're talking about sequences, it's sometimes of interest to be able to look at sums of them to see if there are nice patterns that emerge that we can describe. And when we are looking at arithmetic sequences, there actually is one nice form that we get that I'm going to try and build towards using a story. So this is one of those ones that's pretty well known in math. It might be apocryphal, I'm not entirely sure. But the way it starts is a young child named Gauss was in school, and Gauss was a very talented student, so talented that he actually kind of annoyed his teacher with just how easily everything came to him. It was like he was not learning nothing at all, made them look bad, and it was just very frustrating for everyone. So one day when the teacher was preparing a lesson and Gauss was naturally doing everything much faster before everyone else was getting it done, the teacher just said, "Fine. All right, I'm going to give you something that should keep you busy for the rest of class so that I can have a normal day with everyone else." So the teacher goes to him and he puts on his slate. He says, "Okay, here's what I want you to do. I want you to take all of the numbers from 1 to 100 and I want you to add them up." So something like this, if we're going to use summation notation, from I equals 1 to n equals 100 of the i's. So that's 1 plus 2 plus 3 plus 4, 5, 6, 7, 8, 9, 10, all the way up to 100. And the teacher was pretty satisfied with himself because that takes a little while. This is before calculators. This is when they were doing these things, just add them all up. And Gauss was a kid, not expected to be able to figure these things out easily. Just give him busy work so I can have a nice lesson that isn't ruined by the smart kid. Problem is, well, Gauss was a little impressed, and Gauss ended up figuring this out much faster because, teacher went back to his desk, their desk, and I don't know if it was male or female, and very satisfied. But a couple minutes later, Gauss brings the slate up to him and says, "That was a nice problem. Here's what it is." And the teacher looks at him, like he's not speaking German, because I think Gauss was German, but he looks at him very strangely because he figured it out so quickly. And he says, "Well, how did you get that?" Well, Gauss didn't just add all of these things up slowly. Gauss was more clever than that. Gauss looked at what happened here between these values at the ends and stuck them together. Because he saw that if you look at this in a pattern sense, you'll see that when you take 100 and add 1 to it, you get 101. When you take the next one in, 99, and add 2 to that, you'll get 101 again. And when you take 98, add 3 to that, you'll get another 101. And you can keep doing this pattern all the way until you get to the middle, when you get stuck at 51 and 50, but you'll still get 101, interestingly. And this will end up happening n over 2 times, because you will get half as many terms if you're taking one of each from the top and bottom, where each of these terms, well, in this case that would be 100 over 2, so if you want to be specific, this would happen 50 times. But to get a nice formula here, we could say that this would just end up being that value, 100 over 2, multiplied by what we get in every single sum, 101, because we have 100 over 2, or 50 copies of 101, to get here, which, as embarrassing as it is, I don't know off the top of my head, so I have to actually try and multiply this out myself. You'd have 50, so you carry in the 1, you'd get a 1010, multiply that by 5, and you get 50/50. Which is what Gauss came up with in a couple minutes, because, well, he's much smarter than I am, and even if you saw this pattern, well, congratulations, I guess you're as smart as Gauss was as a kid, but don't feel bad about that. Gauss was one of the best mathematicians to ever live. But the point here is that if we ever want to be able to take the sums of natural numbers, this is a really nice pattern we can follow, because provided we have an even amount that we're trying to add up, the sum of these natural numbers is going to have, well, n plus 1, that's what we're going to have in each of these pairs, multiplied by n, divided by 2. Because there are exactly n over 2 pairs that we're dealing with. And that is our sum of the first n of them. And from this, we can actually derive for ourselves a nice formula for the first n terms of a geometric sequence. That if we want the sum of the first n terms like that, we call that Sn. It's the nth partial sum is going to be equal to n over 2, because we have n over 2 pairs, but now our sums in here, instead of being first plus last in a sense, so you get that n plus 1, here our first has form a1, and our last has form an, because we're not starting at the bottom and adding all the way up. We are starting from some point a1 and going up or down, for that matter, to some point an. But if we want to get the nth partial sum, the sum of the first n terms in an arithmetic sequence, that just follows the pattern n times a1 plus an over 2. And in 10.4, I'll show you another way that we can prove this kind of relationship, this equality here, where instead of going in the Gaussian way with some mathematical cleverness, we'll use a more algorithmic approach through something called induction. But that's getting a couple sections ahead. For now, let's finish with a quick example of how we can use that formula. So for this example, we want to find the sum of the first 10 terms of the arithmetic sequence defined by 5, 10, 15, 20, 25, and then so on. So to do this, we need to first be able to identify our pattern. In this case, we can see that a1 is 5, and our common difference is also 5, actually. So if we want to describe our general term, we would have that an is equal to a1 plus n minus 1 d, where a1 is 5, d is 5, and you can put this in here and check for yourself. We would get negative 1 times 5 plus 5 is nothing, so we'd just be left with 5n in this case. So if we want to find a10, a10 is just going to be 5 times 10, or 50, and as a result, if we want S10, that is the sum of the first 10 terms in this sequence, that would be our number here, 10 times 5, A1, plus 50 divided by 2, or pulling that in, pulling that together, 275. So if we want the sum of the first 10, we can add those first 10 things up to check for ourselves, or you can just use this formula to get that it would be 275. And the last thing we're going to look at for this week is a different kind of pattern we can get with sequences that leads to some other interesting and worthwhile constructions, where we're looking at what are called geometric sequences instead. But we'll get to that next.